pull up a drawing pad. So we talked last time about electricity. We talked about how the electric charge is a conserved quantity. It's a conserved quantity that comes from the local phase invariance of the quantum wave function. So you have a quantum wave function. You can change the phase of that quantum wave function without destroying, like you can choose a different origin for where the quantum phase starts on a given particle. And that, as a consequence, gives you a conserved quantity. However, you have to have a correction because it's a local phenomenon. It's not a global symmetry. So a global symmetry is one where you say, I have a coordinate system that goes on forever in all directions, and I'm able to translate my origin, and it's something that applies everywhere. So because it's a global symmetry, you have a globally conserved quantity within, as long as your coordinate system applies to the system you're looking at, then you have a globally conserved quantity. If you have so time is a global symmetry. These spatial coordinates are global symmetries, provided that your coordinate system has the right properties, meaning that all the spacings are the same size. The difference here is that you have a quantum particle here, and it has its own quantum phase, which looks like e to the I theta. And this quantum phase can be measured relative to an arbitrary position, but that applies only to this local particle. Because it's a local symmetry, the particle that applies here does not necessarily, the phase that applies to this particle does not necessarily apply to this particle over here. It has its own phase, and because these two things are different, it's a locally conserved thing. And so that is, well, because it doesn't apply everywhere, this quantum phase symmetry doesn't apply to all particles simultaneously, you have to make a correction, or you have to add a term to your energy equation. So the energy equation is called the Hamiltonian. It's given by the letter H for Hamiltonian. And this has the kinetic energy. So you have your kinetic energy here. That's the energy associated with the fact that you can have your reference frame moving with any specific velocity. You have potential energy, and you have to have a new one. You have to have a new force right here, or a new term in the energy equation that is related to this local symmetry. So you add it in, and it is EA. It is the electromagnetic vector potential. So this is a matrix instead of just a... So this A has the electric field and the magnetic field in it, and it couples to the electric charge E. So here E is electric charge. That is E is the symbol for, well, so it's a different symbol than this. This E here is E, that is the number, the base of the natural log system, 2.78 something something something. This E over here, even though it looks the same, it's actually not the same. The E over here that looks the same is actually the unit electric charge. So it's the charge on the electron. Well, it's the charge on the proton. The negative E is the charge on the electron. So that's the strength of the fundamental unit of charge of the charge on a single charge particle. And then this A stores both the electric field and the magnetic field simultaneously in it. And so this term here you have to add to the Hamiltonian, and that is the correction that you add to the system in order to preserve the fact that each of these things can have its own unique quantum phase, and that the physics is independent of those quantum phases. If it's a global symmetry, you wouldn't have to worry about that, but because it's a local symmetry, you have to add this back in. Okay, so that is where this comes from. We saw that if you have a moving electric charge, so here's an electric charge that's moving in a particular direction, it will induce a magnetic field that circulates around it. And this is something that depends upon your reference frame, right? So if you have, here's this electric charge, and if you're just staring at it, if you're standing right here next to this electric charge and it's not moving with respect to you, then you don't see a magnetic field. It's only if this electric charge is moving with respect to you that you see that magnetic field, which means that you could have a person right here on a train car that's moving in this direction, and this person would see a magnetic field that's circulating around this way, like that, around this charge, and this person would not see that magnetic field. So the magnetic field, the presence of the magnetic field is depends on your reference frame. So this person that's stationary with respect to that electric charge would not see the magnetic field. This person that is moving with respect to that electric charge would see the magnetic field. That's crazy. So how does well, let me give you an example of something that it happens in real life. Suppose you have, excuse me, a wire. How does this work? So you have a wire like this, and the wire has current flowing in it like this, and you have an electric field that's circulating like this. So I'm sorry, you have a magnetic field that's circulating like this. And if you have a particle, so here's your charged particle that's drifting in this direction as well. So what's going to happen? So here's our reference frame. We are stationary with respect to the wire. There's current flowing in the wire. How does this work? Let's see. So this thing is going to experience a force. It's moving like this. The magnetic field is pointed, in this case, the magnetic field is pointed that way. And so you have V cross B. So this is going to feel a force that pulls it inwards like this towards the wire. So if it's moving parallel, it's going to be pulled in towards the wire. And then the question becomes, what happens if you are moving along with both the current here and that charge? So suppose that you're in a reference frame now where you're standing here, or you're moving in this direction, the current is also moving in that direction, and that charged particle is also moving in that direction. Physically, what should happen is the charged particle should still curve back towards this wire, right? Did I do that right? So V is this way, V cross B, yeah, it goes into the wire. But here, now we're standing, and we're moving along with we're moving along with all of these charges at once. We're moving along with the current, so there's no magnetic field. If we're moving along with the current, then all the charges are stationary with respect to us. So there's no magnetic field generated. We're moving along with this object right here, and so it also should be, well, in principle would be stationary with us, at least instantaneously it's stationary with us. But physics tells us that this person's reference frame and this person's reference frame who's stationary, not moving with the current, they should experience the same physics. So what's going on here? Here's what's going on. When you have this wire, whenever you have a wire, you're going to have a closed loop. So the loop is going to look like this. So you have this loop. Let's see if I'm doing this correct. So you have a loop like this. The current is moving in this particular direction. Would be moving around this way. But if you're drifting along with that loop, with that current, then you would see no magnetic field. And you have this particle here that's moving along also in this direction that would also see no magnetic field. But what does this thing see? Well, it turns out that in special relativity, which is what happens when you transform from one reference frame into another one, like one moving reference frame into a different moving reference frame, relativity tells you that things will contract or expand based upon your relative velocities. So lengths will contract or expand based upon your relative velocities. So here the relative velocity is 0, and so the charges are all equally spread out. So here's all these negative charges here. They're all equally spread out. However, because this particle is, or because this person, the observer, is moving in this direction with respect to this, the current that's flowing back in this direction, all of those things are going to be contracted. Their length is going to be contracted. And so they are going to be even closer together. So you're going to have a whole bunch. You're going to have more electric charges all bunched up here. So you have more electric charges on this side than you have on this side. The density of electric charges is greater over here than it is over here because we are moving with respect to those charges. So because those charges are moving from our perspective, their length contracts and we see them all bunched together. Okay, so now you have a buildup of electric charge over here, and that buildup of electric charge is going to pull this particle in that direction. So that's basically how, even though you might be moving along with the current, you're still going to experience the same physical consequence that you're being accelerated towards that wire. Okay, and it comes down to how do you transform from a reference frame where you are stationary with respect to the loop to one where you are moving with respect to the loop, but stationary with respect to the current in the loop. Length only appears to contract, not literally. Well, but what we see is the appearance. So what we see is the appearance. Now, we haven't done relativity yet, but I can show you why this is the case briefly. So you have, say you have a Snickers bar or a candy bar. So here's your candy bar. It's a space candy bar, and it's moving in some direction. When you look up at this thing, here's you looking up at it, and you want to say how big is that object, you are going to say how big does it appear to my eyeball, which means that the light coming from the back end of it has to arrive at your eyeball at the same time as the light that's coming from the front end of it. So here's these two beams of light coming towards you. However, because it is moving in this particular direction, this one has to travel a longer distance to reach your eye than this one does. So you're not actually, so this beam of light here and this beam of light here are not traveling the same distance, and therefore they can't have been emitted at the same time. If one has to travel a longer distance to reach your eye, then that means that at a given instant from the perspective of someone standing on the space candy bar, the light emitted simultaneously from both ends of this candy bar would arrive at different times from this person's perspective, because this one has to travel a longer distance. Therefore, when you are this person observing the space candy bar moving in this direction, you are actually going to see light from the front of the candy bar that left when the candy bar was back here. So the candy bar was back at this location, and that's when this light left there, and this one left when the candy bar, so there's like position 1 here, and this is position 2. So the light from position 1 left the front, the light from position 2 left the back, and that way they both travel the same distance and arrive at your eye at the same time. And so what we perceive as being, oh, here is the front and the back of this object at the same time, it's actually from someone standing on space candy bar, the light would have been emitted at different times from the front or the back of that. Anyways, the consequence being that because this light had to be emitted slightly earlier, it looks as though space candy bar is going to be contracted along the direction of motion. So it'll be skinnier this way because the light that we see simultaneously here was not emitted simultaneously from the candy bar. And so that is why it should be Milky Way candy bar, yes. So that is why things appear to be contracted. And the question is it literally contracted, or is it appears to be contracted? And the answer, the answer to that is those are the same things. Okay, how something appears from our reference frame is how we measure it. That's the length in our reference frame. So now, I guess if you want to have more dense calories in your candy bar, so you have a candy bar that might be 200 calories, and you want to have fewer bites to get those 200 calories, then you could maybe boost it, and then you would have a skinnier candy bar. Of course, then the problem is that you can't fit the candy bar in your mouth all at the same time. Okay, let's see. So that is magnetism. Magnetism arises from, you get magnetic moments, so like the building blocks of magnetism is, we saw from here that if you have a moving electric charge, so here's a moving electric charge, it will create a spiraling or a curving magnetic field like that. If you were to take an electric charge and circulate it around, so say you have an electric charge here and you circulate it around, what you will find is that the magnetic field will again be circulating around. Am I drawing that the right direction? Well, I guess, sure, I can always pretend. So it will be circulating around in this loop, and you'll see that it points in one direction. All of these magnetic field lines, like this, the direction of the magnetic field, point in the same direction from the center out this way. So if you have a circulating charge, you can set up a magnetic field that is oriented in a particular direction and in a constant direction. If you have a moving electric charge that's moving in a line, then you get a magnetic field that curves around. So you can curve the flow of the electricity and get the magnetic field to point in a straight line, or you can have a straight line movement of the electricity and therefore get a curved magnetic field, or anywhere in between, right? As you twist up the wire or something like that. You can get all sorts of magnetic field configurations. So, but here's the point, is that a circular electric charge, circularly moving electric charge, or some electric charge that is rotating relative to a reference frame, is going to create a magnetic field that points in a specific direction. And this is how you build up magnets. You build up magnets by taking electric charges and orienting all of their rotations, or all the rotational symmetries of those atoms, orienting them in the same direction, and then each individual atom that contributes is going to add a small amount of electric field from that circulation of the electric charge, or the rotation of the electric charge. Okay, so that means that there are two different types of magnetism that you can get. You can get magnetism. So let's say that you have, here's your atom, like this. Atoms look like this. Last time I checked, this is what the actual photograph of an atom looks like. Not really, but let's pretend. And so if you have an electron in this orbital, like this, and it's circulating around, that can create a magnetic field because of the orbit of the electron. So the orbit of the electron can create a magnetic field because that is an orbiting or a rotating electric charge. Okay, now if you have a whole bunch of atoms and they're all lined up so that all of their electrons are orbiting around in the same direction, they all have the same angular momentum state, then they will all add, all of their magnetic fields that those things generate will be adding in the same direction, and so you build up an overall bulk magnetic field from the individual components or the individual contributions of each atom in that object. So this is one form of magnetism that you can get. Yes, the atom is the building block of matter. Now, there's another way of circulating the electric charge, and that is through the spin, the quantum spin of these particles. So spin is a property of the particles that is related to the, well, how much you have to rotate your coordinate system in order to get the phase to advance by 2 pi. So particles that make up matter are called spin 1/2 particles, spin 1/2. So spin 1/2 particles are ones where in order to bring it back to its original configuration, you have to rotate your coordinate system by 720 degrees in order to get 360 degree change in the phase of the quantum wave function. So anyways, the spin also has units of angular momentum that also corresponds to a rotation. In this case, it's the rotation of the quantum phase. And so you can create a small magnetic field because of the spin of the electrons. So not only can you get a magnetic field built up from the orbits of the electrons, but you can also get magnetic fields built up because of the spins of the electrons. So there you go. I did a stream not too long ago where I brought up the fact that you can build an object. So you can take slices, like I guess I'll do 4 slices because that's roughly the shape that I have here. You can take slices of objects that are magnetic from the angular momentum of the orbits of the electrons in the system. And you can take other slices like this, like a wedge like this, but these ones get their magnetism from the spin, and you can arrange them in such a way that all the magnetic fields cancel, but the spins don't cancel. So all the spins are organized in a particular direction, all the magnetic fields are organized in, you choose the magnetic field in one of them to go this way, and then this one goes that way, and then this one goes this way, then that one goes that way, so that all the magnetic fields cancel, but all the spins line up. And so you have a pendulum that, even though it's just sitting there, has a net angular momentum, or has a net spin. And that's pretty weird, but you can do that. So yes, those are space candy bar slices. Let me see if I can pull that up. So it's the spin pendulum, University of Washington. And let's see what kind of images they have available. It looks like this. So each of those, the red and the green, the Christmas colored components of this, the red and the green correspond to magnetic fields that are generated from either the angular momentum of the outermost electron or the spin of the outermost electron. So, and then they're looking for short-range forces that depend upon actual spin, like quantum spin, because that in some environments is a conserved quantity. Certainly with an individual particle, the spin is a conserved quantity. So that's kind of cool. All right, let's see, there's a question here. Do I ever make models of certain system by simulating? If so, what do you use for describing the model, like finite element? So when I do computer models of things, like finite element, I don't build 3-dimensional models of stuff. Our models are more geared towards like simulating the dynamics of a system. So you treat them like point particles, and then you just calculate all the forces that are acting between them, and then you step in time calculate in time, as opposed to like if you're doing a spatial model of something where you might have to break it into different shapes that you use to map out the surface of something. Let's see. Does that pendulum type set up in fusion reactor? I don't know how fusion reactors are set up. I suspect that that's not like that torsion pendulum is really low energy physics. It's looking for very, very weak couplings between things. What materials have non-magnetic abilities? So now, a lot of things. If you have an atom where, so like here's your atom, and you have an electron that's going around this way. If it has a second electron that's going around in the opposite direction, so like all of the electrons, like the spins are oriented in particular directions, so that the spins cancel. So that makes it so that you can't have a magnetic. If all the spins cancel in each of the atoms, meaning that there's an even number of electrons, then the magnetic field that you get from the spin of this electron is going to be counteracted by the magnetic field that you get from the spin of that electron. So there's going to be no net magnetic field from those things. You can also have systems where you have this, the atoms are randomly oriented, like the direction of this thing going around would create a magnetic field like that. And the atom that's next to it, it's going to have a different orientation to its orbits, and so it's going to be pointed like this. And so you don't get domains, like they're not adding up coherently. They're all pointed in random directions, and so individually they might have a small magnetic field that they generate, but collectively, once you get out far enough, they all cancel each other. So that's another issue that comes up. What you'll get is magnetic domains that build up. So you'll have like one magnetic field that points like this, and maybe another one that's next to it that points in a slightly different direction. And these will pull each other into alignment, so they're pointed in the same direction. And then that can cause a kind of a reaction where all the other ones around it will start to align in the same direction to build up magnetic domains. And so you'll have a chunk of metal that has a whole bunch of things that are lined up like this, and then a different domain will have all of them lined up like that, and then the one over here, they'll all be lined up like this, and then over here, they'll all be lined up like that. So you have these different domains, kind of a crude magnet, something like this. So this happens a lot with iron, for example. You'll have magnetic domains that build up in the iron pointing in a particular direction, and then they'll line up in a different direction, because the magnetic dipole that you get from this one atom will influence the one next to it and bring it into alignment. So this is something also that can be induced from the outside. So if you have a magnetic field already that's pointed in a particular direction, and you have a fluid of material where the atoms are free to move around, so they're not frozen in place, but they're free to move around, then you can get all of the magnetic fields to line up with the ambient magnetic field from the environment. So this is how you can measure seafloor spreading. So seafloor spreading, you have well, I guess I'll pull up a map since we might as well do that. Pull up a map with seafloor spreading. If I go maps.google.com. Okay, so there's a question here. Fusion reactors use tokamaks as their magnetic setup. Yes, that's correct. But a tokamak is basically a device that has a magnetic field in it that is used. The magnetic field in a fusion reactor is there to prevent the circulating electron or the circulating charged particles from hitting the walls, so that when they get close to the wall, the magnetic field deflects them back into the volume. So it's a way of, because the stuff circulating around inside of a tokamak or a spheromak, the different fusion reactors, is so hot, they're moving so fast that they would melt through the walls. So you have to contain them with this magnetic field, which is not a trivial thing to do. If it was a trivial thing to do, it would have been done already. It's not a trivial thing to do. So you have to have very high quality magnetic fields. Not only do they have to be strong enough, but they also have to be uniform enough. Like they have to have the proper shape so that these particles can't leak out the side. What was I talking about? Oh, the Mid-Atlantic Ridge. So here we go. We'll open up this thing so that we can see the Mid-Atlantic Ridge. Here's the Mid-Atlantic Ridge right there. And we can tell, I know there's a way to turn the clouds off, and I can't ever remember how it is. I don't know how to turn the clouds off, but there's some way to turn the clouds off. So maybe I'll just zoom in until they disappear. So the way that we know how rapidly the seafloor is spreading is because, or let me rephrase that. we see the seafloor spreading. We can measure the spreading of the seafloor, which is about 1 centimeter per year. So the seafloor spreads at roughly the rate that your fingernail grows. Fingernail grows at about 1 centimeter per year. The seafloor spreads at about 1 centimeter per year. So if you're going to travel across the ocean, you want to do it quickly because it's getting farther apart, and you'll have to travel an extra, if you wait 100 years, you'll have to travel an extra meter in order to get there. So that is the rate that the seafloor is spreading. So then the question becomes, how often does the Earth's magnetic field switch from one direction to another? Right now, the magnetic field on the Earth points towards the south. So the magnetic North Pole, what we claim to be magnetic north up in Canada, is actually the south pole of the Earth's dipole magnetic field. And the North Pole of the Earth's dipole magnetic field is in the southern hemisphere. So, and the way that you can tell this is because the compass needle points to the north, which means that it's attracted to the magnetic south pole. So the Earth's magnetic south pole is in the northern hemisphere, the North Pole is in the southern hemisphere, and then these switch. As the Earth evolves, the liquid core goes around, all sorts of convection and things like that are happening in it, and you get the dynamo that dynamo effect inherently is going to have some flipping of the magnetic field. The sun flips its magnetic field every 11 years. For the Earth, it's every 100,000 years. So the magnetic field of the Earth flips over, and the question is, how often does it happen? How do we know that? I just told you that it happens every 100,000 years. How do we know that it happens every 100,000 years? The answer is, you can look at the orientation of the iron deposits in the ocean floor. So the rocks come out, they have some iron deposits in them. If you have the Earth's magnetic field currently pointed to the south, then all the iron deposits are going to line up because they come out in a molten state, which means that the iron atoms can align themselves with that external magnetic field. So all these things are going to line up like this. Okay, and the seafloor spreads apart, and you get this trail of, or this chunk of iron deposits in the oceanic floor that are all lined up in the same direction. Then, in the past, or in the future, this is going to switch directions. It's going to be pointed upwards. So this flips over. Now it's pointed this way. And so now the new iron filings that are coming up at where the crust is spreading apart are going to be lined up in this direction. And so when you look at the ocean floor, so here is the seafloor right there, and you have bands. Okay, so this is the oceanic ridge. I'll draw it nice and thickly like this. So that's the oceanic ridge. It's spreading apart like this, and you'll have bands where coming out to either side, it'll be roughly symmetrical, where these filings all point this direction, and then these ones all point this direction, and then these ones out here all point this direction, and et cetera, and so forth. And so you say, okay, how wide are these? And at 1 centimeter per year, that means that it stayed like this for 75,000 years, stayed like this for 100,000 years, it stayed like this so far for 120,000 years. And you can map out the expansion history, or you can map out the history of the orientation of the Earth's magnetic field by looking at those things. Okay, some questions. The Earth's core is basically molten iron. That depends. The Earth has two cores. The inner core is solid. The outer core is molten. So it has like a spherical shell of molten iron in the core. And that's where the magnetic field is generated, which actually means that the Earth's magnetic field does not go directly through the center of the Earth. So the magnetic field is generated, you have to have a conducting fluid. And so there's the solid inner core right here, the liquid outer core right there, that's where the magnetic field is generated. You have to have a conducting fluid in order for the magnetic dynamo effect to turn on. And so the Earth's magnetic field actually comes through the core like that. It doesn't go through the center of the Earth's core, it goes through the outer core. And as a consequence, the Earth's magnetic field is displaced a little bit. So if you look at the Earth and you look at the charged particles that are trapped near the Earth, so the North Pole, or the magnetic South Pole, or what we call north, is in just north of Canada, or it's in Canada, but it's on the extreme north end of Canada. And the South Pole like sticks out down by the Falkland Islands. And so if you were to look at a side view of the Earth, so here's a side view, you have the magnetic north up here and the magnetic south kind of like that. So the Earth goes like that. The center of the Earth is like right here. And so the Earth's magnetic field comes into the ocean at a slightly different angle in the middle of the South Atlantic Ocean. And you get what's called the South Atlantic anomaly. So there you go. That's the South Atlantic anomaly. It shows up as basically the magnetic field lines are coming in at a weird angle relative to the surface of the Earth, and so compasses stop working. Here's the view. This is the picture I was trying to draw. I want to open it in a new tab. So this is the picture I was trying to draw, kind of unsuccessfully. Oh, I had it pointed the wrong direction. So anyways, here is the rotation axis, is the green one. And then here's the magnetic field axis, which is the magenta one. And then the charged particles trapped in the Earth's magnetic field come in roughly perpendicular to the surface to produce the auroras in the northern hemisphere. In the southern hemisphere, because that's where it's farthest from the rotation axis, you get them coming in at kind of a strange angle right here, and that creates the South Atlantic anomaly. So that's pretty cool. It would come in at an even more weird angle if the Earth was flat, so I guess this is further evidence that the Earth is round. Okay, let's see. I want to make sure I answer any questions that come up. Does space have its own magnetic field? So the Earth has its own magnetic field, the Sun has its own magnetic field, the solar system has the sum of the magnetic fields of all the component planets. The universe, or like the galaxy, has its own magnetic field. The galaxy's magnetic field is actually kind of broken up into domains. So when you have cosmic rays going through the galaxy, it will bounce around in those different, it will be affected by the orientation of the magnetic field in different domains. So space on its own, like vacuum, does not have its own magnetic field. The magnetic field of the galaxy is built up of the sum of the magnetic fields of all the components. So I don't think that the galaxy has its own mechanism for creating it doesn't have its own individual dynamo. It's the sum of all the dynamos, like it's the sum of all the components of the circulating charges in the stars and the planets that are in the galaxy that build up the galactic magnetic field. And so each one of those things individually will flip. The stars will flip their magnetic fields, but the galaxy itself does not have its own dynamo, and so there's no mechanism for the whole galactic magnetic field to flip over, as far as I can tell. Let's see. Does the flip of the poles on the Earth have a significant effect? So if the magnetic poles on the Earth were to flip, it goes through a period. It's not like the whole thing just flips instantaneously. It goes through a period where it turns into higher multipole fields, so you get something that looks like this. So here's the Earth, and right now we have a magnetic field that points basically, well, it actually points the opposite direction, so I might as well draw it the way that it actually points. It points like this, and what will happen is as the field reorients itself, it will break up into a variety of magnetic domains that are pointed in these different directions as they all kind of rotate their way around and then point in the opposite direction. So in that transition process, you go from having a dipole magnetic field, a dipole meaning two poles, a north pole and a south pole, and it will build up a magnetic field that is more complex. You build up like a quadrupole and an octupole magnetic field. A quadrupole would have four poles, so you have like a north-south like this, and so the magnetic field here would be, have a different shape. It's usually the energy in the field, I think, is basically the same, but the strength of the magnetic field in any given direction falls off more rapidly. So dipoles, the magnetic field of the dipole falls off relatively slowly as you go farther away. When you have a quadrupole, the strength of the magnetic field falls off much more quickly as you get farther away. The reason being that these things kind of cancel each other, right? You have a south pole kind of next to a north pole, and so they somewhat cancel each other as you get farther out, and so it's harder to distinguish the structure of the magnetic field. And then you'd have an octupole, so you have like a north, south, north, south, south, north, south, north, like this, that's connected to form like a cube. And it can be oriented in different directions. It's basically the electron orbitals. You can have the magnetic field fill up the same shapes as the electron orbital shapes because it's a spherical coordinate system and you're decomposing it into a superposition of many magnetic fields that all are that form a basis from which you can build any shape in 3 dimensions, a spherically symmetric coordinate system in 3 dimensions. So, and the set of functions that we have that does that are called the Bessel functions, and that's where you get the electron orbitals from, the spherical Bessel functions. Anyways, the point being that it goes through a more complicated structure for the magnetic field. That implies that your magnetic field, like the charged particles trapped in the Earth's magnetic field, are going to go from being in these toruses, in these belts that are going around the Earth, coming in at the North Pole and creating the northern lights. It's going to be happening everywhere. So you're going to have, instead of having an Earth like this, where you have the magnetic field looping around like that, and so particles come in and hit the northern hemisphere and the southern hemisphere and create the northern and the southern lights, you're going to have a magnetic field that has stuff coming in and out from all sorts of directions. And so you'll get the effective northern lights all over the planet. So it'll be kind of cool to watch. Be like, oh, there's some over here, there's some over here. You might be able to see multiple instances of the northern lights as you go through it. And you might die younger because, you know, now the radiation is closer to the surface of the Earth, and so you're going to be bombarded by some of these charged particles. I mean, life has survived these transitions. So life has existed on Earth for billions of years. The magnetic poles switch every 100,000 years, and so there's been tens of thousands. Is that right? Billions, 10 to the 10. And then we've got this thing at 10 to the 5, and so you've got hundreds of thousands of flips of the Earth's magnetic field. So it's you. Sorry I hung up on you. Okay, let's see. There is a question here. Just thought, do protons and neutrons, by way of being made of three quarks up and down, have some internal polarization similar to how some molecules are naturally charged but have some polarization? Okay, so you can get things, you can get magnetic dipoles. You can measure like the magnetic dipole of the neutron that's related to if there's some, if the neutron has some coherent structure in the orientation and the spin properties of the quarks, so that they're not randomly oriented within the neutron, or there's some excess probability that the quarks will be aligned in a particular direction, then you would create a natural dipole moment in the neutron. So we can measure, so here's your neutron, you've got three quarks in it, those three quarks have their own spin properties, they have their own electric charges, and so yes, you could imagine that nature favors a particular type of configuration of the quarks in a neutron, and as a consequence, you get a stable neutron electric dipole moment. It turns out that you don't get this. So these things are essentially randomly oriented, which means that a single neutron doesn't have a long-term stable dipole magnetic field coming from it. That's actually one of the reasons why there's motivation for the axions. So if the neutron were to have preferred orientation of the quarks, like their spins aligned in a particular way or something like that, then that would violate CP. You get CP violation in the quark sector. So you get CP violation from the quarks and from the gluons, the gluon field that actually make up most of the energy inside the neutron. So you have this quark and gluon field. If there's a preference for how these things are all related to each other spatially, like how they're spatially arranged and also how their spins are arranged, then that would violate CP, because if you switch all the charges, then all of a sudden the dipole flips over. And so this should exist. You should have, in principle, CP violation in the strong nuclear force. But the fact of the matter is, and so that would create an electric dipole moment. You make measurements of the electric dipole moment of the neutron, and you get something very, very, very small. So you can't say that it's definitively zero, but you can say that it's much smaller than the theory would have predicted that it be. And so that shows that the strong force does not actually have CP violation, at least in any appreciable amount. And so how do you get the strong force that should have CP violation, and then you get something that it turns out that it actually doesn't have CP violation? And the answer to that is you invent a new particle, and that particle is called the axion. And I don't have my, oh, here it is. That particle is called the axion, like this, named after this dishwasher detergent because it cleans up the strong CP problem. And that's a candidate for dark matter that the thinking people invoke for their dark matter candidate. But turns out, so in principle, in theory, you could have a preference for particles being aligned in a particular way inside the nucleus or inside the nucleons themselves. Turns out that it doesn't show up. And so these things are randomly oriented to a very high degree, which is not predicted. You would predict that there would be some preference for them all lining up with each other, but it turns out that there's a significant absence of such collusion between the quarks in a neutron. All right, let's see. Is lightning possible in a vacuum? No. Let's see. Well, maybe. Yeah, I suppose that you could get lightning in a vacuum by polarizing the the vacuum. So in a vacuum, okay, we're getting a little bit off topic, but that's fine. In a vacuum, you can have the production of particle-antiparticle pairs. So here's the vacuum. You got basically nothing going on, and then spontaneously you produce an electron-positron pair like this. So you have E plus, E minus, and that makes a plasma. So if you have enough energy, enough ambient energy in the vacuum, then you could spontaneously produce lots of these particle-antiparticle pairs that would then give you a plasma through which you could get a bolt of lightning. I don't know what that would take, like what kind of energy densities it would take to make that happen, but you can, if you provide enough energy to the system, that energy would come in the form of an electromagnetic field, right? So you have this really super strong electric field, and there's energy in that electric field, and then you can use the energy in that electric field. That electric field means it's a bunch of photons. You can use that energy from the electric field to spontaneously produce. So here's a photon coming along, spontaneously produces an electron-positron pair, and then here this comes back out. This is a plasma, right? It's a positronium plasma, and then you could get a lightning bolt through that. But I don't know what they call it, like a dielectric constant. I don't know the details of the physics of this. Sounds like something that would be asked on the GRE, but I don't know what it is. Okay, does gravity and magnetic pull have something to do with each other? No. So Fox 2 answered that question. That's a great question. Are the electromagnetic force and the gravitational force related to each other? And the answer to that is no. They are different forces. They couple to different charges. So the electromagnetic force couples only to electric charge. So if you have a particle that has electric charge and no mass, then it will couple to, of course, these particles don't exist, but we can pretend, then it will couple to the electromagnetic field and not to the gravitational field. By the same token, if you have a particle like a neutron, so here's a neutron, the neutron has mass, but it does not have electric charge. So the neutron will couple to the gravitational field, but not to the electromagnetic field. So you can have particles that couple to one and not the other. And so they're completely independent forces, and they come from completely independent symmetries. So the electromagnetic force comes from that local phase invariance of the quantum wave function. Gravitational force comes from, well, we don't have a quantum theory of gravity, so there's no, I'm going to use that as the excuse for me not being able to come up with a good analogy for it. So, okay, let us keep going. So we talked about the magnetic field. We talked about figure out quantum gravity on stream, just like do it in front of everybody. That would be great. This is an interesting thing, the Hall effect. So one of the things that you find if you have a wire that's conducting electrical current through it, that the wire behaves the same if it's positive charges that are flowing in this direction or if it's negative charges that are flowing in the opposite direction. So there's no difference fundamentally in the current flowing in a wire. If you have a positive set of charges flowing in this direction, then you'll create a magnetic field that circulates around this way. If you have a set of negative charges that are flowing in that direction, then you also get a magnetic field that is oriented in the same direction. So those two things are equivalent. The positive charges moving one way is equivalent to negative charges moving the opposite direction. And so how do you know which one is actually moving? If you have an electric current, how do you know which direction the current is actually flowing? Like, not so much which direction the current is flowing, because that's assigned by convention to be the direction of the positive current. But how do you know which charges themselves are actually moving? Is it the positive charges that are actually drifting through the wire, or is it the negative charges that are drifting through the wire? Now we'll say, oh, well, we know it's the negative charges, but the question would be like, how do we know it's the negative charges? If there's no difference between the two, how can you tell which one is which? How can you tell if it's the negative charges that are drifting through the wire or if it's the positive charges that are drifting through the wire while the negative charges stay stationary? And the answer to that question is the Hall effect. So the Hall effect is how we determine the sign of the charge carriers. And that's also how we know that the charge carriers are the electrons, the negative charges. Okay, so here's how that works. You have a wire coming in, you have a block of material like this, a wire coming out, and then you run a magnetic field through this. So there's a magnetic field pointing in this direction. Okay, so what's going to happen? Say you have an electric charge, you have a current flowing through this, so you have these positive charges. We're going to do the positive electric charge paradigm moving in this direction. What's going to happen? Well, the positive charges moving in a magnetic field is going to create, the magnetic field is going to create a force that causes them to drift. It's called the Lorentz force. The force is equal to Q, the electric charge, like these electric charges, times their velocity. So there's a velocity of them moving in that direction, cross the magnetic field. So that's it tells you the direction of the motion. V cross B tells you the strength of the interaction is the product of the velocity and the magnetic field, and the direction of that is assigned by this cross product. So V cross B is V in this way, cross that way. So if it's positive charge that comes in, then these things will, V cross B is going to cause them to drift up like that. Okay? If it is the negative charges that are changing, then what's going to happen? So this is a positive, we have a positive current flowing in this direction. Okay? That could also be produced by negative charges flowing in this direction. Okay? So if you have a negative charge that's flowing in this direction, then what's going to happen to these negative charges? So now their velocity is backwards. Their charge is also backwards. So you have, in this case, you're going to have the force is equal to, the magnetic field is still pointed in the same direction, is going to be minus Q. So because they're negative charges now instead of positive charges, it's going to be minus V cross B. Okay? You have two minus signs. You change the sign and you change the direction of the motion, which means that those two minus signs cancel, and the direction of motion of these of the negative charge particles is also going to be like this. Okay, so the positive charges will drift towards the upper end, so you'll get a pile up of positive charges here. The negative charges will also drift towards the upper end, right? So it's minus Q, and then you have minus V, minus V cross B, hold on. Minus V cross B is going to have a force that goes down, and then the minus Q changes the sign of the force and also drifts them upwards. And so you'll get, if it's a negative charge that is flowing, then you'll get a pile up of negative charges up here. And because charges have to be conserved, if you have a positive charge carrier, so you have protons moving through this thing, then you're going to build up positive charge on this side. So this is with a positive charge carrier. So if it's the protons that are drifting, you'll get positive charge here and you'll build up negative charge there. And so you'll be able to measure the voltage across this. Like, what's the electric field going in this direction? In this case, you'll get an electric field that points this way, because you're building up positive charges here and the leftover negative charges are down there. So if it's a positive carrier, then you get an electric field that points in this direction, and you can measure that electric field. So you hook it up to a voltmeter and you measure the electric field. If it's the negative charge carrier and the charges are flowing in this direction, then what you'll get, so with the negative charge carrier, it's coming in this way, you get minus Q and minus V, which means the force is pointing in the same direction, and so you're going to build up negative charges along that surface and positive charges down here. So now when you measure that voltage, right here, here's your voltmeter, you get an electric field. It will tell you that the electric field is pointed this way. So this is called the Hall effect. So you have this thing set up with a magnetic field threading through it so that the electric charges are driven to one side of that object. And if the electric field points that way, then you know that it's the protons that are causing the electric current to flow. And if the electric field points this way, then you know that it's the electrons that cause the electric current to flow. And it turns out that it's the electrons that flow. The electrons are the things that are moving through the wire to make the electric current. And so, anyways, that's cool. That is the Hall effect. And it wasn't until the Hall effect was developed that we actually knew the sign that the electrons are the things that move around. Let me see. There's a question in here. The force carrier of the electromagnetic force is the photon. Yes, the electromagnetic force is mediated by the photon. That's how, so these charged particles that couple to the electromagnetic field, that coupling is the coupling of the photon to those charged particles. And the field that is produced by the presence of this charge is the electromagnetic field. So you have this photon field surrounding your charged particle. And the other particles in the vicinity interact with that, like macroscopically interact with all the photons that are around there. So the photon field is the how the electromagnetic force is mediated from one point to another. Let's see. this gets me wondering, since the weak force are related, electromagnetic and the weak force are related, shouldn't their force carrier particles also be related? Electrons are fermions, though. W and Z are bosons. So electrons are fermions, that is true, but the photon is a boson. Okay, so let me go into, as long as we're on the subject, we'll do electroweak symmetry breaking. Okay, so, and I'm going to basically spill everything that I know about this. There are some details that I know the answer to, but I don't know why that's the answer to them. And so this is going to be pushing up to the extent of my knowledge, but we'll go for it anyways. So the electromagnetic force has a force carrier, that's the photon. Okay, the weak force has a force carrier as well, and that is called, there are three of them, the W plus, the W minus, and the Z naught. Okay, so this is the electrically neutral one, and these are the positive and negative charged intermediate vector bosons. So the electromagnetic force, the photon couples to the electric charge, so, or Q, I guess I'll write it as Q. Okay, so the photon couples to the electric charge. So anything that has an electric charge will couple to the photon field. That's, there you go, that's how that works. The weak, anything that couples to the weak force will couple to these WZs, W plus, W minus, and Z naught. So the charge that's associated with the weak force is called the weak isospin. Isospin. Okay, now the weak isospin is basically what you do in that case is you say, well, the way that I learned it, and this was a long ago in a galaxy far, far away, that basically the neutron and the proton, if you ignore the electromagnetic field, so there's no electromagnetic field, and as a consequence, there's no way to tell that one of them has electric charge and the other one doesn't. You basically say, okay, these two things are essentially the same. They're roughly the same mass. If we ignore the electromagnetic field, because we only care about the weak field, these two things are basically equivalent to each other. You can rotate between the two. And so there's a conserved property of the fact that you have these collections of quarks. And that conserved property is weak isospin, that you can transform from one to another and that the interactions basically stay the same. The weak interactions basically stay the same. As you go from a proton, you can basically say, I'm going to switch a proton and a neutron, and my weak interactions are going to stay constant. So that's weak isospin. So each of these things has a charge called an extra charge called weak isospin. And because of that weak isospin, it can couple to the W and Z fields. Okay, so that's kind of the best I can do on that. Maybe at some point in the distant future, I'll go back and relearn all this stuff. Okay. Then the idea was that because the weak decays arise from the fact that it's electrostatic repulsion that kind of destabilizes the nucleus. Is that right? Because that's an alpha decay, but a beta decay. Anyway, so there was some insight that said, oh, maybe the weak force and the electromagnetic force are actually related to each other. Some of it had to do with as you approach an electric charge. So like here's an electric charge right here. If you measure the electric charge way out here at a distance, you get the value E. But if you measure the electric field or the charge on this electron, and you do this by Gauss's law, this is what we talked about last time. So you can build a sphere, a surface around that electron and measure the electric field that comes out of it. As you measure the electric charge in a volume closer and closer to the location of that charge, so it's located at some point in space, if you do the same Gauss's law experiment, as you get closer and closer to the electric charge, you find that the charge changes. So when you're way out here and your Gaussian surface, like the thing that you measure the electric field through, at a large distance, you get this value E. That's the charge on the electron that we know and love. But as you get closer, it turns out that the value of this charge, so the value of E, as you go to distance, so this is distance here, it's going to be here at large distances, this is the value of E, but as you go to smaller distances, it actually rises. Okay, it rises slightly. The reason that it rises is because there's this vacuum electromagnetic field. And because you have a strong negative charge here, as you get closer to it, the electric field gets very strong because there's this electric charge there. the spontaneous production of electron-positron pairs, so here's an E plus E minus pair, as these things are produced, you're going to preferentially produce the positrons pointed towards the center. So here's an electron-positron pair that forms. The positron will form closer to the nucleus and the electron are closer to this one. So let's say that this is an electron right here. I should have given you the quantity. So this is an electron, it's got a negative charge. When you spontaneously produce an electron-positron pair in the vacuum region around that electric charge, you will preferentially have the positron closer to it and the electron farther from it. So in general, these two things are, they cancel each other out because it's exactly a positive and a negative charge. And so at a great distance, those two charges cancel each other out. Their effects cancel out. But when you're at a very close distance, then when you draw this surface down here, you find that there's a whole bunch of extra positive charge in that area, which means that these positive charges are shielding the actual value of the negative charge there. So you have to account for that shielding because the vacuum doesn't contribute to the charge on the electron itself. So it contributes, if you add everything together, it contributes out there. But if you actually want to say what is the charge on the electron all by its lonesome self, then you don't count these things. So the value for the electric charge that you measure at a distance includes the contribution of all of these particles. But as you get closer and closer to it, you're going inside of that boundary, and you're getting fewer and fewer of these positive positrons that are forming out of the vacuum, spontaneously being produced out of the vacuum. And you get closer and closer to the actual value of the charge, the bare charge on the electron. And so it's got to be a larger charge because at a larger distance, it's being shielded by the positrons that are forming close to it. It polarizes the vacuum. You get extra positive charge near the electron. Those extra positive charges shield you from the full might, the full strength of the electric charge. So this is called a running constant, a running coupling constant. So as you measure it with higher energies means that you can probe closer at closer distances. As you measure it with higher energies, the value of the electron charge on the electron grows. And it turns out that the weak nuclear force had a similar property, and so you run them back, and it turns out that the two meet at the same point. The values of the strength of the electric charge and the strength of weak isospin meet at some point, and so you get a unified theory. So that was some of the insight that went into like why these things should be related to each other. And it turns out that the fundamental theory, the electroweak theory, the combination of electricity and magnetism and the weak nuclear force, there are still 4 force-carrying particles, but those 4 force-carrying particles are not the particles you think they are. You have instead the W plus, which we've seen. There's the W minus, which we've also seen. And then there's a thing called the W naught. Okay, and then there's a particle called the B. So this has an electric charge, this has an electric charge. Those things remain, as you cool to lower energies, these things stay the same. As you go to lower energies, these two things, because they have similar quantum numbers, some of the quantum numbers are the same. In particular, their electric charges are the same. That means that these two things are interchangeable with each other, and you can choose a particular orientation, or the universe can choose a particular orientation of how much these things mix with each other. So basically what you would say is, okay, here is the B and here is the W naught. Okay, so some particle has some amount of B-ness to it and has some amount of W naughtness to it. And because these things have the same electric charge, when you're looking at the electromagnetic force, they are indistinguishable from each other. They don't couple to the electric field, so there's no way that the electromagnetic field can tell which one you're working with. Therefore, you can have a particle with any superposition of these two axes. You could have a particle that's is here that's some amount of W naught and some amount of B, and a particle over here that's some other mixture. Okay, so as you go to lower energies, what happens is the universe actually chooses that some orientation between these two. It chooses a mixture. The mixture that it chooses has some angle associated with it here. So here's this angle. It's called the weak mixing angle. And that angle is how much did the universe want to rotate the W naught and the B into some other orientation. And it chooses this angle to do one thing. So basically what you get is you have one particle that is a sum of these two things. So you get some particle that is equal to W naught times sine of whatever that angle is plus b times cosine whatever that angle is, and you get another particle that is W naught cosine theta plus b sine theta. There might be a minus sign in here somewhere that I'm missing. It's not important. The minus sign thing isn't important. It's just that these things are some mixture. Maybe this has the minus sign with it. Let's pretend that that one has the minus sign. I don't know where the minus sign actually goes, but I'm sure there's a minus sign in there because that's the nature of these rotations. So you have two new particles, one that is a superposition of the W and the Z like this, or I'm sorry, that's a superposition of the W and the B like this, the W naught and the B, and the other one that is this other superposition. And it turns out that one of these has no mass. So let's pretend that it's this one that has no mass. I don't know which one it is, but one of the two has no mass, and we call it the photon. And the other one has actually slightly more mass than it otherwise would have, and that is the Z. So the Z is one combination of the W naught and the B, and the Z has slightly more mass than the W that started with, because the B particle itself has some mass, and now you're getting like all the mass added together. And so the Z is actually heavier than the W plus and the W minus. And that's why it's a different particle, because you would think, why didn't they call it a W naught? And the answer is there is a W naught, but it's the superposition or the combination of that gives you the massive combination of these two things that give you the Z, and so that contributes there. And it's the massless combination that gives you the photon. So the photon is this weird superposition of two things where the masses essentially cancel, and you're left with just the energy. So that's kind of weird. So that's electroweak theory, kind of at a fundamental level. Well, as best as I can do, because I'm not a quantum field theorist. It's a bit outside of my expertise. But that's essentially what's going on. You have this weak mixing angle, and that determines these things. And it drives you to the angle has to be such that the masses of these two particles cancel to give you a massless photon. So if we were to measure very precisely the mass of the photon, there are constraints on the mass of the photon. You can do experiments that measure the mass of the photon. If you measure very precisely what the mass of the photon is, and it turns out that it's non-zero, then that tells you what this mixing angle has to be. But so far, all the measurements of the mass of the photon have turned back something consistent with zero. So our best estimate is that the photon is indeed exactly zero. But you always want to, push kind of the frontiers of physics. That's an assumption that we're making. It's just that every measurement that we've made with increasing improvements comes back with something consistent with zero. So we don't have any reason to think that it isn't zero, other than the fact that it could be non-zero. Okay, so let's see. Anyways, that's where how these things are related to each other. The W and the Z bosons are related. They're all bosons. They all have integer spins. The photon has spin 1. The W and the Z also, I think, have spin 1. And I think they have to have spin 1 so that their spin properties are preserved with this transformation. Okay, so I don't know if I missed anything. Is the direction based on the stronger of the two? That angle is, they chose a coordinate system, and that mixing angle is relative to the coordinate system they chose. They chose like W's in this direction, B's in this direction, then there's this angle that gives you these two different mixtures of them. And that's all just a convention in terms of how that was done. Weak isospin is the name of the conserved quantity that's associated with that. Yeah, the virtual part doesn't add to the to your electric bill. That's true. Okay, so that is what were we talking about? Okay, so that's where the photon field comes from. A couple to these different things and electric charges. So there we go. All right, what else do we need to talk about? So I think that is the origin. So we know where the origin of the magnetic field comes from. We know where the origin of the electric charges come from. We know that there is a field that couples electric charge and magnetic fields. Like there's an electromagnetic field that is the combination of both of these things. We know that. Okay, here's a question. I always thought that the photon had to be zero mass to move at the speed of light. That is true. That you can only move at the speed of light if you have zero mass. So the B particle that is the weak nuclear force, or I'm sorry, the electroweak force quasi-photon looking thing. I don't know what it's got a name. Well, the name is the B particle. I don't know if it has another name. That one does not move at the speed of light because it does have some mass. But the photon, and at the low energies that we live in, the photon has no mass. Otherwise, it wouldn't move at the speed of light. You can have a universe where the speed of light is not the speed limit; it's some other speed limit, so you don't need to have photons in order to have special relativity. You can invoke special relativity with any speed limit that you want and get the same result. Okay, let's see. Let me come back to the book and see if we missed anything. So we did the Hall effect. I'm not going to worry about forces and torques on current carrying loops. That's not all that interesting. So let's talk a little bit about what happens, where does the energy go when you have current and electric charges moving around and being bottled up and located in different places. So in particular, so you have these electrons that are moving around. We know that there are electrons that are moving now. The electrons are moving, and you can set up something. We'll use the chemical symbol for battery, looks like this. Okay, so this is the chemical symbol for a battery. Battery. All right, you have the plus end over here, you have the minus end over here. The convention is to always follow the direction of the positive charges. So what's going to happen? You have this positive charge here. So that positive charge is going to be reflected. The current is going to flow this way, and you're going to pile up a whole bunch of positive charge right here. So this is all metal except for the battery. So here's your battery. You have all this metal. The electric charges are going to move through the metal wire. They drift actually kind of slowly. The electric charges drift fairly slowly through the metal wire. And we're going to assume that the metal wire has no resistance to the flow of the charges. That's not true. If you take a look at the cross section of a wire, you have all these atoms that are in there, and as the electrons bounce around, they bump into stuff. And as the electrons bounce around and bump into stuff, that slows down their flow. And they deposit energy. So here's this electron, it comes along, it collides with this atom, that causes this atom to start shaking. So here's the shaking vibrations of that atom. And so that takes energy out of the system. Electron comes in, bumps into an atom, knocks it around a little bit, it starts to shake. That's thermal energy. That is not electrical energy. And so this electron loses some energy there, bumps into something else, causes it to shake, loses some energy there, bumps into something else, causes it to shake, loses energy there. And so you're actually generating thermal energy from the bumping, like the crowded nature of these things as these electrons bump into stuff as they drift along in the wire. Okay, so that's resistance to the flow of electricity in a wire. Okay, we'll go into a little bit more detail about that later. Just the point of it being that when electrons are drifting through a wire, they are bumping into things. That causes those things to vibrate. That vibration is pulling energy out of the electric field that provided the original energy and dissipating it into the thermal energy. And so there is some energy loss for stuff moving through the wire. However, in general, it's relatively small, and so for the most part, you ignore it. You can't ignore it all the time. It's just that it comes up in certain circumstances more prominently than other circumstances, and so it depends upon your circumstances. So if you're talking about transmitting electricity across thousands of miles in a conduction line, then you actually have to worry a lot about the losses of energy from from the fact that these aren't perfect conductors, like that the electrons have some resistance to them drifting through the wire. But if you're talking about the electrical circuit in a radio or something like that, then it's a lot less resistance relative to the amount of energy that you have available to you in the battery. So the battery has a voltage. Okay, the battery has a voltage, and the voltage is the potential. It's the same potential that like the gravitational potential is. If you multiply the voltage by the charge, QV, that gives you an energy, right? Energy is, you have some potential, which is the field from some quantum force that you have, or some force that you have creates this potential. And then if you couple to that potential, the product of your charge that coupled to the potential and the strength of the potential itself gives you your potential energy. Okay, that's the energy that you have because of your location in space. So I'm located at some space. That space has some fields going through it. The fields that I couple to, I add the strength of my coupling and the strength of that field to get my potential energy. So that's going to be mgh So GH is the function of the potential in a uniform gravitational field, and I multiply it by m that couples to GH, and that gives me mgh, which is potential energy. Here, voltage is the potential, and I multiply it by the charge, and I get the potential energy, Q times V. Okay, so anyways, here's this battery. The positive electric charges are going to flow out of the positive end. They're going to drift over here, and they're going to pile up right here, because right here, this is a metal plate, and this is a metal plate, and there's air. There's nothing in between them. So there's nothing that allows them to connect to each other. And as a consequence, you're just going to build up electric charge on one side, and you're going to deplete the electric charges on this side. So charge gets built up on one side of this and gets depleted on the other side of this. And what you're going to end up with is you're going to create a potential across this that is going to be equal to the opposite of the potential of the battery, right? So this battery here is going to have some voltage, like a 1.5 volt battery or a 12 volt battery or a 9 volt battery or whatever the case may be. And across these two metal plates, there's an opening in the thing, so there's no current flowing through. There's an opening in it. Across these metal plates, you're going to build up a voltage that is exactly equal and exactly opposite. Once it fills up, once this thing fills up, it'll be exactly equal and exactly opposite. So you're going to have minus V going across this thing. This type of metallic structure is called a capacitor. So this is a capacitor. TOR. Okay, and it stores this electromagnetic energy. It builds up a potential as you fill up charges on it on one side and the other. And it turns out that the energy that you get from this, it looks like this. It's QV, like that. That's the energy that fills this up. Let's see, is it at some point along the way, we're going to, this would be important to know, that the energy is proportional to, the energy across this capacitor is proportional to the amount of charge on the capacitor, how much charge has been built up on either side. That's what's important. The energy across this gap, the energy in the electromagnetic field across that gap is proportional to the amount of charge that is stored by that capacitor. Let's see. There's a question here about the Aharonov-Bohm effect. I won't cover it now. I actually would have to go back and revisit it myself in order to do that. But at some point, I should cover that. Okay, so this is the energy that you get built up across some length of this wire from the fact that you're piling charges on one thing and dissipating it from another, or removing it from the other. You can also have a circuit set up that looks like this. So here's your battery. Again, that's the chemical symbol for battery. Here is your loop. And you can have some object here, like a hot dog shaped object, okay, where as the electric current flows through the wire, there's no losses, or we're going to pretend that there's no losses when in fact there are losses, but we'll pretend that there are no losses as the electric current flows this way. But once it gets to this hot dog shaped thing, then it runs into all sorts of stuff. It starts bouncing around, bumping into stuff. Okay, and so it transfers the potential energy that it has as it's drifting through this electric field. And then it hits this thing and it starts heating it up. So this gets warm and starts radiating energy away. It starts dissipating energy out of the system. And then it comes over here and then eventually comes into the back of the battery. So again, you have a potential difference, and it's only differences that matter. So all the way from the beginning, we've been saying that energy, potential energy in particular, is the energy that you have based upon your position, and you can choose your origin. You can always choose that, here's a hill, and I'm going to choose this to be 0, and so I can have negative potential energy down here. I can have positive potential energy up here. I get to choose my origin when I describe a problem. And so the only thing that really matters is the differences in energy from one point to another. It's that difference that matters, not where it's located, because that's an arbitrary choice. Like physically where it's located is an arbitrary choice. So the same thing is true here. When you look at the voltage on a battery, it'll be like 1.5 volts. That's a typical AA battery. That 1.5 volts is the difference between the voltage on that side of the battery and the voltage on this side of the battery. Or in other words, the voltage between this thing that has the protrusion on it and then the flat part at the back. That'll be 1.5 volts. So that only tells you the difference between here and here. It doesn't say what's the ambient voltage in the environment around it that you would have to add to the system. It doesn't ignore that. It only says what's the difference across one battery terminal and the other. So this is 1.5 volts. When I circle all the way around this loop, I have to come in at 1.5 volts lower than where I started. Okay. So here, there's going to be energy lost as I pass through this hot dog shaped thing. That energy loss is going to cause the voltage to drop across this gap, or across that obstruction. So in other words, the potential energy is going to fall as I go down here because I'm dissipating that energy away. I have potential energy up here. This is all smooth sailing. There's no friction or anything like that. So this is all at the same height, same value of the potential, same voltage. And once I get here, then I start losing that energy by converting it into thermal energy and radiating it away. And so I'm losing energy as I traverse all the way along here. And then I get to this thing, and then it's smooth sailing again. There's no resistance in this simplification. Okay, so that means that the voltage needs to drop as I go across this resistor. Okay, and so the voltage drop across the resistor is proportional to how much current there is flowing through the resistor. If there's more current, then I'm going to dissipate more energy. So the energy that I have dropping across this thing, so I guess the energy dissipated, is going to be equal to the current. The current tells me how much is going through times the, let's see, that's not what I meant to do. It's the voltage that I care about. The voltage is going to be equal to the current times the resistance. Is there another way to think about this that's more valuable? No. Okay, we'll go with this one. So now there's this joke that goes around in physics circles where we make fun of all the engineers, where they're like, oh, there's 3 laws of electricity. There's V equals IR, there's I equals V over R, and there's R equals V over I. And then we say, ha 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 ha, the 3 laws of electricity, ha ha ha. And we laugh at them at their expense. And I'm sure that they don't mind. Okay, so anyway, so the amount of energy that is lost, the drop in the voltage that you get is the current times the resistance. So the more resistance you have, so resistance has units of what, volts per second or something like that, because, or volts times second, so that the current has units of charge per second, and it has to cancel that so that you eventually get electric charge or electric potential. Okay, anyways, the moral of the story being that if the current goes up, if there's more current flowing through this at a given resistance, then the voltage drop across this will be larger. The only way to get more current flowing across that is to increase the voltage of the battery. So the voltage dropping across the resistor has to match, exactly has to match, the voltage across the battery. And so that tells you what the current is going to be. That's how you measure current, is basically you say, okay, here's the voltage drop that I feel across here, and here's the strength of the resistor that I'm putting it across, and the current is the only thing that's left over. So I measure 1.5 volts across. So the voltage is the drop in the potential, just like a drop in a gravitational field, except this is the electromagnetic field. And then I put my own resistor across. If I have a voltmeter, I put my own resistor across it, and I measure, and I can measure the current like that. Okay, so well, actually, what you do is if I want to measure the voltage across I have some resistor, I want to measure the voltage across it. Then what I'll do is I'll put something in there where it has a resistance that I know what it is, and then I measure the current, and I multiply those things together, and that tells me how much the voltage drops. So if I have multiple resistors in a circuit, so here's my battery, goes like this, and I have a resistor here, and I have another resistor there, then the voltage, the total voltage drop across both resistors has to match exactly the battery. Because otherwise you would not conserve energy anymore. As long as energy is conserved, then this voltage drop here has to match the voltage gain across the battery. Okay, so anyways, the moral of the story being that resistors drop the voltage, and the voltage in that case is going to be equal to the current times the resistance. Another way to think about that is current is the flow of electrons. So that is E dot or Q dot. Okay, the dot is the time, the rate of change with time. So Q dot is the change in the electric charges with time times R. That's going to be important. This formulation is going to be important. The last thing that we need to talk about is that we know that flowing charges create electric fields or magnetic fields. So you have a wire here, and you have a magnetic field that would be circulating around that wire as the charges move in a particular direction. So here's this magnetic field that's circulating around the wire. If I coil the wire up, so I make a wire coil like this, I can make a magnetic field that lines up in a particular direction. Okay, so here's this battery like this. Battery looks like that, coming like this. And the charge is going to flow through this battery, and it's going to generate a magnetic field. Okay, so far so good. This is just a wire. If we assume that there's no or very little resistance, it's just a wire. So if you plug a battery into this, it's just a single wire. And as the electric current flows, there will be a huge amount of current that flows. So you have a voltage here. The voltage on your wire equals IR. And there's going to be some, in this case, we have to disband the approximation that we had that there's no resistance in the wire. There's some small amount of resistance in the wire. So this is going to be very small. That R is going to be very small, which means that the current flowing through it, because everything has to match when you get back to the end, the current flowing through the wire is going to be enormous. So you get a huge current flowing through the wire. Your battery dissipates very quickly because it's basically shorted out. And then I guess you're done at that point. You need to charge it up again. So this coil of wire is simply a wire. Once it gets going, then it flows with no resistance. However, if you change the voltage here, so if you like have the wire or have this battery and then you flip its polarity, or you oscillate it back and forth, or you adjust it somehow with a knob, then you're actually going to be changing the current that's flowing through the wire. However, you've built up, when you initially engage this circuit and plug it in, you build up this magnetic field. So there's a magnetic field. Because the current is flowing through this wire and that wire is coiled up, you're going to generate a magnetic field. And there's energy in that magnetic field. And so when you switch it in the opposite direction, you have to dissipate this energy. You have to take the energy out of the magnetic field and put it back into energy going the opposite direction in the magnetic field. So you build up this magnetic field that looks like this. If you switch the direction of these things, the system is going to resist that change. And so you have to remove all the energy from this magnetic field that you built up and then point it in the opposite direction. And that takes time. It takes time to do that. So it resists the change in the electric field. So this thing here is called an inductor. Inductor. And it doesn't really change things, electric fields that are, it doesn't really, what am I trying to think? It doesn't affect the voltage when you're in a circuit with a single battery, like a fixed battery, a fixed voltage. So you have a voltage here that stays constant. It's going to build up that electric field fairly quickly, like a matter of probably microseconds. Builds up that magnetic field, and then it's just going to sit there, and nothing's going to change. But if you start messing around with the voltage here, you start changing it from one side to the other, then you have to contend with the fact that you have to remove energy out of the magnetic field that's pointed in one direction and put it, rearrange that magnetic field, and nature resists that. Okay, and so, anyways, that's an inductor. So an inductor, you actually can get a drop across this inductor, even though it's a conducting wire all the way through. There's a resistance to the change. There's a resistance to changing this voltage, and that resistance, so it's a resistance to the change in the current. So you get an energy that's built up across this inductor that's related to the speed with which the current is changing. So if the current changes rapidly, then there's a very strong resistance to that rapid change. If the current is changing very slowly, then there's a weak resistance to that change. So the voltage that drops across this coil of wire is going to be related to the rate of change of the electric current. So in this case, it's going to be, the value of the inductor is given by L. Not like we haven't used L for a whole bunch of other things, but anyways, that's what it is. The voltage is going to be the change in the current, so that's I dot times L, or that's also equal to Q double dot, right? That's the acceleration of the electric charges. So this resists the acceleration of the electric charges times L. Okay, so now we have all of these individual components. Like these are different things that you can do with a wire. Okay, so let's say that we have a system that has all of these things in it. So we have, and let's take a look at the voltage or the potential So we're looking basically at energy. So basically we're looking at the energy of the system, potential energy for a unit charge. And we're going to get something that looks like this. The voltage drop across an inductor is Q double dot times some constant, L. The voltage drop across a resistor is going to be Q dot, that's the current, times the resistance. And the voltage drop across a capacitor, which was that parallel, the two plates, the metal plates that weren't touching each other, is going to be Q times, it turns out to be 1 over the capacitance. So there's going to be, let me back up. There's going to be something that is, Q times 1 over C. Okay, and this is equal to voltage. Voltage. This is going to be, I just ruined it. There. Back up, voltage. So all of these things are the voltage that you have going across each component. So if you have a circuit, here's your circuit like this, okay, and you have an inductor, you have a resistor, and you have a capacitor like that all lined up. These are the voltage drops across all of those things. If you set up a DC circuit so that there's only the flow of electricity through the circuit by itself, and there's no change in the electric circuit, then that means that this thing goes to 0. There's no acceleration in the electric charges. They're just moving with some speed through the system. And that will cause some resistance and will cause charge to build up on the capacitor. So now what happens is you can start this equation here. This equation here is very, very interesting. Why is this equation interesting? And why is it very, very interesting? So let me rewrite it again. Q double dot L plus Q dot R plus 1 over, or Q times 1 over C is equal to the voltage. Okay, and this looks very familiar to the following equation, which is mx double dot plus bx dot plus kx equals force. Okay, so this is the force that you experience in a mass in a spring. So if you have a mass, here's a spring, here's the mass attached to the spring, and there's air resistance. This is ma, mass times acceleration, is the sum of the forces, and then we move all the forces to the other side. So one of those forces is the spring force. So the energy that's stored in the spring is, that's an arrow, by the way. It looks like a backwards letter J, but that's an arrow. The energy stored in the spring is related to, or the force on the spring is related to its displacement from equilibrium. Okay, so the more you displace that from equilibrium, the stronger the force will be. And it's got a minus sign, but then when you move it, so MA, so mx double dot is equal to the sum of all the forces. Force plus, so this is an external force, plus the spring force, plus the other ones. These have a minus sign, like the resistance has a negative sign, the spring force has a negative sign over here, and then you add them, move them to the other side so that you just have the external force on this side and all the internal forces on the other side. So this structure for this equation, it's actually MA equals the sum of all the forces. But then you're saying, I want the internal forces to be over here, and I want the external force to be on this side. Same thing is going on here. I want the internal voltages to be on one side and the external voltage, so the thing that I apply to the system, my battery, is going to be on the other side. So these are all internal components to that equation, and then this is the voltage that you get from the battery or from your power source. So, but it's got exactly the same structure. You've got essentially a term that's an acceleration, you've got a term that is a velocity, and you've got a term that is a displacement. It's a displacement of the charge in this case. And in one case you get a force, in the other case you get a potential, which is like the gradient of a force, or the integral of the force. But these things are balanced. Okay, so that means that the solution to a mass on a spring is exactly the same as the solution to the charges in the electric charges in a circuit. So you're going to have all the same responses of that circuit. So if you have a mass on a spring, so here's a spring like this, and it's got, there's air resistance in there. If you start wiggling that spring up and down, so here's your hand, here's your grubby mitts, wiggling that spring up and down, you can get the spring to respond in all sorts of ways. Any way that you can get the spring to respond, you can get an electric circuit to respond. with the same kind of outside driving force, except that now, instead of a driving force with your hand, what you get is a rotation of your reference frame that I did not want to have happen. So now we have a system that can behave exactly the same way that a mass on a spring can behave. So you can set up a resonance. You can get a response where if you drive it at exactly the right frequency, you get a very large response in that system. So this circuit that has, it's called an RLC circuit, R, so that's resistance, L, inductance, C, capacitor, a circuit like this, and now we're going to hook it up to a variable voltage. So instead of a battery, it's plugged into some kind of variable power source where we can fluctuate the voltage. We need to be able to fluctuate the voltage if we want to get a Q double dot. So if we want the inductor to play a game, to play in this game that we're creating, then we need to have a variable input source so that we can get an acceleration of the charges, not just pushing the charges, but actually accelerating the charges. Not just having the charges move with some velocity, but having them move with some acceleration. So we have to be able to vary that. Okay, so this system, an RLC circuit, RLC, is a circuit where you can get this exactly the same kind of responses that you get so here it's the voltage. In the other case, in here it is the motion of the charges. And for the case of the mass on a spring, it is the motion of the mass. It's the position of the mass. So how much displacement you get on the mass on a spring as you drive it is the result. You're looking for basically x of t. And in this case, you're looking for q of t, how much charge is circulating. And in particular, q is actually the charge that's built up on the capacitor. But it's how much electric charge are you putting into something. Here, the displacement is how much force are you putting, how much displacement are you adding to the spring. So you have this spring mass, damped spring and mass system that you're oscillating up and down and getting some kind of response, whether it's a resonant response or whatever. What you're measuring is how much displacement are you getting from the mass from the equilibrium position of the spring. So this x is related to the displacement of the mass relative to the equilibrium of the spring. This q is the displacement of the charge relative to the equilibrium position of the amount of charge in the capacitor. Okay, so those are the two things that we're measuring. So you're basically measuring how much charge is on the capacitor or how much displacement you have on the spring. So you can set up a circuit. You can drive that circuit with some external voltage, because that's, in this case, it's the voltage equation that we put together. The voltage has to be conserved as you go around the loop. And then that tells you, okay, how much energy is being dissipated by the resistor, how much energy is being dissipated by the inductor, or how much motion is being forbidden by the inductor, how much the acceleration of the charges is being resisted by the inductor, and how much charge is built up in this capacitor. Okay, so you can tune this circuit. You can choose elements in the circuit. You can choose the resistance that you want to have. You can choose the number of loops in your inductor. You can choose the size of your capacitor in order to have it respond very favorably to specific resonances, to specific frequencies. Just like you can choose your mass, you can choose your spring, so that if I drive it at this rate, I want to get a gigantic response. And that's how you can set up something that can detect very weak signals. This is basically what you have in the old time radio dials. So you used to have a radio dial. You'd have a radio like this, had a little needle that moved across on your radio dial, and you had the volume thing over here, like this is the power and the volume, and then this one was the tuner. And that tuner, you would rotate this tuner and it would slide this arrow across this dial, and it would tell you what frequency you were tuning into. The way that it works is this dial right here, if you look behind that dial, it's connected to a capacitor like this, except it's a capacitor that's specifically designed so that it has basically metal plates. So it has all these metal plates like this. And as you twist the capacitor, these metal plates will interleave with each other so that eventually they'll go like that. So you can separate the plates and have very little charge that's built up between them because the plates are kind of separated from each other. Or as you tune the dial, you can increase the amount of charge that gets built up in that capacitor, how much charge gets stored amongst all these metal plates. So you're attaching to a capacitor where you can adjust the voltage across that. You can adjust the amount of charge that the capacitor can hold. As a consequence, you can adjust the frequency that this responds to, and then that frequency just happens to correspond with whatever is written on the dial. So if you want to listen to 1380 kilohertz, then you adjust the capacitor so that the response is like adjusting the spring strength. It's adjusting how strong the spring is. So you might say, I want to oscillate this spring at this rate. I want to oscillate this spring mass system at this rate and get a gigantic response. I want a huge resonant response. So then what I have to play with is how stretchy is the spring that I'm working with. If I have one that's too stiff, then if I move it up and down, I'm going to not get much response. It's the difference between the response relative to equilibrium is going to basically be zero. If the spring is really stiff, then it's going to stay at the equilibrium position no matter what. If it's too stiff, then it might as well just be connected with the bar. If it's too floppy, then I'm going to wiggle this up and down, and the mass is just going to sit there. So that's the opposite extreme, which I don't want. What I want is the spring to be chosen specifically so that when I oscillate it at my chosen frequency, that I get a huge response. So this variable capacitor is the equivalent of adjusting the strength of a spring on one of these mass systems, like spring mass systems. And where you get the biggest response, then it only takes a small oscillation to get the big response. If it's tuned properly, a small oscillation will generate a big response. Just like the wind blowing across the Tacoma Narrows Bridge, which is exactly the same spring mass type situation, except that now it's a different kind of oscillation. You can get a big response even though it's a small perturbation. Same thing's going on here. A small perturbation, like say from a very distant radio tower. So here's a very distant radio tower that's broadcasting at some specific frequency, but you're miles away from it. You can be hundreds of miles away from it. I can pick up Salt Lake City radio stations from where I live. So that's like 400 miles away from where I live. So 400 miles away, there's this very weak signal, but it's connected to a circuit that responds at that frequency, that's designed to have a large response at that frequency. And so I can tune in to that thing. So there you go. That's how analog or radios work. Even digital radios, I think, are built essentially the same way, but that's how that works. Okay, I'm out of time, so let me quickly go through this, any questions that I can pull out, and then next time what's going to happen. So on Thursday, we'll be talking about some more details about all these electrical circuits, like where this comes from, so Maxwell's equations, and then we'll talk from Maxwell's equations, we'll go on to electromagnetic radiation, and we'll investigate the nature of these circuits under the when we're considering the whole response of the electromagnetic field, which is actually pretty interesting. Okay, so let me see real quick. Coiling up the wire more does give you more energy in that inductor, but it's an energy that you build up, it's a potential that you build up as you're trying to accelerate the charges in a different direction than what they were already going. And that will come up next time when I give more details on that. So AM/FM radios. So I'll talk about AM/FM radios next time as well. So remind me to talk about AM and FM radios because it's kind of interesting. Does adding radio receivers add more power needed by the radio station to power the more radios? That's a good question. So my suspicion is that the radio receiver actually drains a tiny amount. So like KSL in Salt Lake City is 50,000 watts, I think. 50 kilowatts, I think, is what they're broadcasting. So they're broadcasting 50 kilowatts. My suspicion is that the amount of energy consumed by a single radio is like probably microwatts or milliwatts. And so, yes, the more people that tune in, it would basically limit the distance over which the signal can propagate. But you're talking about, if you look at a typical urban area. So here is Salt Lake City, and here's your radio tower that's broadcasting stuff, and it's going out in all directions. And then who's listening to it? Well, this person's listening to it. So you have all these people that are spread out over here. And while on the grand scheme of things, this person will remove energy from that system in this particular direction, which makes it so that the signal doesn't propagate quite as far. If you're talking 50,000 watts, and let's say each one absorbs a milliwatt, or like even 5 milliwatts. So that's 0.005. Okay, so the question is how many people listening simultaneously can you supply with a single radio station? I'm sure that it's less than 5 milliwatts. I'm sure it's way, way less than 5 milliwatts. It's probably 5 microwatts. But let's pretend it's milliwatts just so that we can get a conservative estimate. Okay, so then if I divide these two, that should give me, this is the watts and that's the watts per car. And so if I divide that one by that one, then I should get the number of cars. and I get what, 5 times 10 to the, I get 1. 5's canceled. It's 10 to the minus 3, and that is 10 to the 4. So that's 10 to the 7. 10 to the 7 is what, 10 million? 10 million cars. And it's probably 10 billion cars that you could pick up from that. So that's what's going on. Let's see. I didn't think we were supposed to tell you what they're drawing in Pictionary. I'm an expert at Pictionary, especially because I can't write words, but I don't write words anyways. Let's see. It shouldn't matter. The transmitter signal. Yeah. So when you have a transmitter, you basically choose the wattage that you want. Most of the energy gets dissipated by being absorbed by the environment. So it gets absorbed by the trees and the grass and reflecting off of stuff and bouncing around. So the overwhelming majority of the energy is going to be lost in the atmosphere, wiggling just random electrons that are flying around, wiggling those things. It's not going to be what's lost in the cars. It could be what's lost in the cars if you have a closed environment where the cars are the only thing there. So when you build your own radio station, you're going to choose a transmitter with like some amount of power. You have to get a license probably for some power. And then you're just going to blast it out and people are going to pick it up. And you want as long as you blast it out with enough energy that it doesn't matter who picks it up, then there's no limit to your audience. There's no practical limit to your audience. So it is true what was said there, that you basically just choose your transmitter power and then you just broadcast. That's what, you're broadcasting, you're spreading it out broadly. And then most of that energy is just dissipated into the atmosphere. Let's see. Yeah, and so we'll get into how wireless phones charge and stuff like that as well. Can we transmit electricity like a thing? I know there's plenty of energy in our airwaves. Can I harness the local energy like Tesla coil? So the Tesla coil, Tesla's statement about, charging things, you can charge at a distance. You can induct heat from a distance. But the efficiency is not what Tesla originally thought it was. And so it's hard to do it over long distances. It's a lot easier to do it over short distances. And we'll see next time how that is done. Okay, unfortunately, I really got to take off. I can't stick around any longer, but I appreciate everybody's time. I hope that this was worth your while. Let me see who we can raid. I'll be back on Thursday. We'll pick up kind of where we left off, and we'll go into Maxwell's equations and then see the details about how everything works.